lesson on potential dividers, and it draws on all the ideas that we use for basic circuit theory, but it just asks you to draw upon more than one idea at once, so that's where the difficulty lies. You have to start drawing along many ideas. So let's start with the basics so we're familiar with them again. I'm going to start with a really simple circuit diagram, but potential dividers are characterized by having two resistors in series with one another. So let's just talk about how that will affect a circuit. So really basic and easy stuff we start with. This battery is a 6-volt battery, and it's providing well, no, let's not talk about the amps yet. Let's just talk about what 6 volts is. 6 volts means that there are 6 joules going to every coulomb that's going around the circuit. So if I were to imagine, and this, I know this model isn't perfect, but if we follow this model, all of the problems we'll have in A-level physics will pop out quite neatly. So coulombs, which are a group of electrons, are coming out of the battery and they're floating around the circuit. They get to one resistor and they use up some of their energy through the resistor, and then through the remaining resistor they use up the remainder of their energy. And then they go back to the battery where they need to be given more energy again. In actual fact, 6 joules of energy on each of these coulombs. We definitely know that they've lost all their energy here. They're going along with no joules. You might ask, why is it that they're able to move if they've got no joules? That's a very good question. But let's just stick with the theory at the moment. This model at the moment, they come round and they go back with no energy at all. The battery recharges them. Okay, to make life easy, I'm going to make these resistors identical. So they're identically hard to get through in effect. So how much energy do you think would be used in one of the resistors? Well, if they're equally as difficult, then 3 joules would have been used up, leaving us with 3 joules. And the remaining 3 joules are used up, leaving us with no joules. So that leaves us with a very nice simple circuit. The key to this is that what we're interested in is we're looking at the voltage, or, as we're going to call it from now on, the potential difference about each of those resistors. So PD equal to the potential difference. In other words, it's looking at the electrical energy at one point on each coulomb and the electrical energy at the other point and looking at the difference between the two. In this case, how much is there? Well, there's 3 joules on each coulomb that's being used up. So 3 joules per coulomb is the same as saying 3 volts. Similarly here, what's the electrical potential difference between these 2 points? Well, once again, the difference is 3 joules on each coulomb, or 3 volts. Now that doesn't matter as to what the current is or anything, that's just a nice, it's easy to work out because it's a nice share. If you've got the same resistance, then half the energy must be used in the first, over the first resistance, and the remainder of the energy in the second. Interestingly enough, in a series circuit, if you add together those, they must equal the input energy. You can't be left with anything at the end. It must be used up in totality over the 2 of those resistors. Now, if we have, let's say we have 0.3 amps flowing through this circuit. What does 0.3 amps actually mean? That's the definition of the current. Of course, 0.3 amps is the current, which means 0.3 coulombs are flowing around the circuit every second. I hope these 2 definitions you'll be able to recite. You should be able to. They define the electrical circuit and actually everything else that's associated with it. So if you know the definition of the voltage and the current, the rest should be straightforward, or at least you won't fall into any traps. So 0.3 amps means that 0.3 of these coulombs are shunting around every second, Doesn't matter how much energy they've got in them, that doesn't matter at all. Think of them like train cars moving around. This is how much speed the train cars are going past. The amount of coal that the train cars are carrying is how much energy they have and how much they give up to each of those respective resistance. Okay, hopefully what will be recall from memory is the equation for Ohm's law, or any version of that, if we are. I mean, I don't like encouraging the use of triangles, but if you are having trouble with this, that's want to get you on a sure footing to start with. Voltage, or potential difference, we should be saying, is current times resistance. However, in this circuit, which differs from the GCSE circuits, because we've got two of them, this actually refers to the total resistance we have, which in this case is the voltage divided by the two resistors added to each other, or... Okay, so if I wanted to work out how much resistance was in each of these, I could say to myself quite happily, with a slight rearrangement, I hope we're happy with that, that up to there and that down to there, we have 6 volts divided by 0.3 amps, giving us 2R equals 20 ohms, or each of them 10 ohms. Okay, good. So that just recaps basic circuit theory. Now what we're going to do is we're going to start varying these resistances so they're no longer equal. Let's take a look at the next one. So all other things being nice and equal, we still have a 6-volt battery. That means it's delivering 6 joules to each coulomb. I'm now going to make one resistor twice as resistive as the other one. And now we're going to try and work out what the potential difference is about each of these by one of two methods. So let's just write down the methods to start. First one is by working out the current in the circuit, and the second one is the use of some simple ratios. And you can use either of these to work out potential differences in the future. So let's do both of them and see which one you feel more comfortable with. First of all, we have the coulombs coming out of the battery, charged with energy. How much energy? 6 joules, because it's a 6-volt battery. They come around, they give up some of their energy, and they leave uncharged, no energy, and they head back to the battery to be given some more energy. Okay, so first of all, let's work out what current we have floating around this circuit. Okay, current is voltage divided by the total resistance. In this case, we have 6 volts divided by 2 lots of one resistance plus the other resistance, which gives us 6 divided by, bearing in mind this is 10 ohms, we have 30 ohms. And that gives us 0.2 amps. Okay. A good starting point. Now, what we can say is, we can then say that the potential difference around one of them, let's call this one the 2R, is equal to the current times the resistance of the 2R. Because remember, the current is always the same in a series circuit, so the same current flows through this 2R resistor as flows through the 1R resistor. So let's just follow that through. Current is 0.2 amps multiplied by, well, I know R is 10, so we've got 20. and that gives us 4 volts. Okay, what's the potential difference in the 1R resistor? Well, the very easy way of saying that is we know that 6 volts need to be used over the 2, so simply it's 6 minus 4, which gives us 2 volts. Because those two must add together to be 6 volts. However, longhand, let's just make sure that works. The current times the resistance of the 1R gives us 0.2 times the current, which is, the resistance, which is 10, sorry, which is 2 volts. Okay, so there we go. If you're unsure of how to do it, this method is fail-safe. In effect, what's happened is, across this resistor, 4 joules have been used up per coulomb, leaving us with 2, and the remaining 2 have been used up over the second resistor. So we work out the current, and then use that in the equation V equals IR. You can work out the respective potential differences between the two. However, the ratios method might be a little faster. If you're familiar with that and you can do that in your head, then ratios might be a little better. Let's take a look at how you do it with ratios. With ratios, what we're saying is, let me just draw out that circuit again. This is number 2. We know that over these 2 resistances, we need 6 volts to have taken place, 6 volts to have been used up. We also know that the ratio of the potential differences is the same as the resistances. So the ratio of potential differences must be the ratio of the resistances. So in other words, and we know what these are, by the way, it might be easier if I write 20 ohms there and 10 ohms there. Let's write PD1. So therefore, I now have PD1 over PD2 is going to equal resistance 1, let's call this one number 1, this one number 2. 20 over 10 must be the same as PD1 over PD2. But I know that those two must add together and be equal to 6. So in other words, I need something which adds together to be 6, and one of them to be twice as big as the other one. So the only way that's possible is if potential difference 1 is 4, and the other one is 2 volts. I did that quite quickly. However, maybe if you're mathematically minded, that might be an easier and quicker way to do it. The ratio of the potential differences is the same as the ratio of the resistances. Okay, now, we're going to go back to method 1, about the current, but we're going to write it down algebraically. In other words, rather than using actual known values, I'm just going to call this one V. I'll call this one R1, R2, and the current going through is I. Now, how did we work out the potential difference here? Let's call this PD1. Okay, PD1 is the same as current times resistance number 1. However, I know that the current is the voltage divided by the total resistance, which is the voltage divided by R1 plus R2, because I'm adding those two resistances together. So in other words, if I substitute this into here, V over R1 plus R2 times R1 gives me the potential difference. Or if you want, V over R1 plus R2 by R2 gives me P D2. These are algebraically identical to what we did in the first instance. And I'll prove to you that much because what we will do is we will just quickly, in a bubble up here, test that theory out. PD1 is V over R1 plus R2 times R1. Let's see. 6 volts in over 20 plus 10 times 20, giving us, actually that's 30 over 30, 2/3 of 6, 4 volts. Don't believe me? Try it for yourself. Which is exactly what it is, 4 volts. Good. Okay. This equation is one you're probably likely to see, but you'll probably like to see it in a slightly different way, and I'll draw it slightly differently. If I turn this on its side, you're more likely to see potential dividers drawn like this. V out, you take the output, V in, R1, R2. So V out is the current, which is the V in over the two resistances, multiplied by R2 in this instance because it's across there. And that is the equation for the potential divider. Why is it used, you might ask? Well, if you have a voltage, a certain voltage coming into a circuit, but you only want a bit of it coming out, you have to put it in a potential divider. If there was only this circuit, and the battery was across here, though you might vary the current, you would always get the same voltage out as was in. So you need to put two in series with each other, so this voltage is shared between the two. And that's great use for a potential divider. So, some examples. Let's see how we get on them. Okay, let's try this one. I'll give you two examples. 6 volts. Let's do 10 ohms and 20 ohms. And I'm looking for the output. Think you know the answer? Hit pause. Otherwise, here comes the result. Okay, let's do it first of all algebraically with the potential divider equation. We want V out, which is the same as V in over R1 plus R2 times the second one. So 6 over 10 plus 20 times by the 20 gives us 4 volts, similar to the last one. However, if we want to do it by ratios, we could simply say to ourselves that 10 over 20 must be the same as, say, V over V out. So this is V. But I know that these two must add together to equal 6. So I'm looking for one is a ratio of 2 to the other. So therefore V out. Right, let's try another one. This time I'm looking for 2 ohms, 6 ohms, I have a 24 volt input. What's my output? Think you know, hit pause, otherwise here comes the answer. Right, algebraically, V out equals V in R1 plus R2 times R2, which gives us 24 over 2 plus 6 times 6, so that's 8. That's 6 over 8, which gives us 3 over 4, which gives us 18 volts, I believe. Yeah. Now, if we want to do it by ratios, of course, I could say to myself, right, well, this gives me a total of 8. So I've got a quarter of it here and 3/4 of it here. So I need something that's in a ratio of 1 to 3 that gives me 24. Well, my common denominator is 6. And therefore I've got 3 lots over here and 1 lot of it over there. 18 to 6 volts. It's easier to do it in your head, and when you become more confident with it and confident with maths, you can see why that is. Okay, now potential dividers don't just stop here. It just seems like a quirk, an electrical quirk. They actually are far more useful when you start to add in sensors. When I see electrical sensors, I mean the following. You're happy that that is, of course, a resistor. I hope you're happy that this is a variable resistor. Now those aren't sensors, but here are the sensors. There's the first one, which is an LDR, a light-dependent resistor. And this behaves, it changes its resistance as the light levels change. So if it were the light to increase, i.e. it becomes bright, the resistance goes down. Whereas if it was to become dark, like the light levels go down, the resistance, in actual fact, goes up. Now I hope you can see how this starts to become useful here. You could replace one of these for a sensor and start to vary the resistance. What about this object here? The one I described as like a hockey stick. It's actually a thermistor. It behaves differently with temperature. So let's imagine this became hot, i.e. the temperature has gone up, the resistance goes down. If it becomes cold, well, the temperature is coming down, the resistance in actual fact goes up. The way I like to remember both of these is thinking that if you're putting energy in, the resistance is going down. If you're putting energy in, the resistance is coming down. Whereas if you're taking energy out, resistance increases. Taking energy out, resistance increases. Okay, let's think about this in the context of a potential divider. Let's throw in now one sensor and one resistor, and let's look at what happens to the V out. Okay, then, this obviously changes with light levels, so let's imagine darkness were to fall on this system. What happens to the voltage out? Well, if darkness falls, then the resistance of the LDR goes up. Now, resistance of this goes up, then a larger proportion of the energy, or the voltage, is shared across here than it is here. So V out goes down. Okay, what happens if I have a thermistor here? An ordinary resistance. Okay, let's say it gets hot. If it gets hot, the resistance of the thermistor goes down. So therefore the V out. So now this has gone down in resistance, so this is a bigger resistance comparatively. So a larger proportion of the voltage is dropped over here. And of course vice versa occurs. If light falls on this system up above, then the resistance goes down, so V out increases. And if it gets cold, resistance of the thermistor increases, and so the V out decreases. So suddenly you have a sensitive system that's starting to change its output dependent on the conditions that are falling on. And why is that important? Well, you can get systems like diodes and transistors that trigger at certain voltages. So a condition change can trigger a circuit to set something off, i.e. street lamps, or if you're in a home, a thermostat setting off the heating if it gets too cold, etc., etc. Very interestingly, a question could be, what would happen if I changed that system the other way around? What happens when it gets dark now? Well, now this resistance increases here, so therefore the reverse occurs. So swapping those around can cause the reverse change to happen. Right. I think it's worth looking at a question, example here. This one might need explaining, but if you feel confident with the material, then you might want to try this one cold. Let's say cold. Let's take it. Okay, we've got 1 kilo ohm resistor, and I've got an LDR attached to 5 volts, and I have an output. Now, when it's dark, the LDR is 9 kilo ohms resistance. When it's light, the resistance of the LDR is 1 kilo ohm resistance. What I'd like to know is what's the maximum and minimum output of that voltage given a light and a dark condition, or if you like to say, what's the output voltage when it's dark and what's the input voltage when it's light? If you think you know, hit pause. Otherwise, here comes the answer. I'm going to call it D for darkness. Okay, for darkness, remember, our equation is, because now it's getting a little bit more complicated with the numbers, so let's work back to the equation. V in over R1 plus R2, multiplied by, let's call this R2. So that gives us 5 volts over, and it's dark now, so we're at 9 kilo ohms and 1 kilo ohm, so therefore it's 9 kilo ohms plus 1 kilo ohms multiplied by, this is the 9 kilo ohms because it's dark. So that's 9/10 of 5, which gives me 4.5 volts. Okay, brilliant. What about V out when it's light? Well, let's do the same sums again, but this time just remember what we're let's see what we're adding in here. When it's light, it's 1 kilo ohm, so we have 5 volts over 1 kilo ohm plus 1 kilo ohm multiplied by 1 kilo ohm, which gives us actually 5 over 2, 2.5 volts. So that's quite interesting actually. We're getting a share of 4.5 over 2.5, so only that range. We're not accessing anything lower than the 2.5 volts. We can't get a 1 volt in this system. We could, however, if we change the voltage at the resistance at the top. And so therefore in some systems you might have a variable resistor there. So you could change it accordingly, so you can get exact precise voltages output. Okay, one more example. Okay, this time we've got a thermistor. And this time I'm putting a thermistor at the top. And I've got a 20 ohm resistor in there. 6 volts coming in. At 80 degrees Celsius, the V out is 5 volts. So what's the resistance of this thermistor if the output's 5 volts? A little bit more complicated now, but if you think you know, hit pause. Otherwise, here comes the answer. Okay then, slightly more complicated. So let's build up this equation again. V out is V in R1 plus R2 times R2. So we know our V out, which is 5 volts. We know our V in, which is 6 volts, over. We've got 20 here, plus an unknown, and the R2 is 20 there. So now some serious rearranging needs to happen here. I'm going to take all of this, stick it at the top, and bring that back down. Exchange those two. So I've got 20 plus R3 equals 6 over 5 times 20. 6 over 5 times 20 gives me, what's that? That's definitely 4. 6 times 4, 24 R thermistor. And I can minus the 20, only 4 ohms. So it's 4 ohms when it's hot. Okay, second part. Let's say that when it's cold, or 20 degrees Celsius, the resistance is equal to 24.5 ohms. A bit of an odd number, but I want you to start using the calculator now. What's the V out? Think you know? Pause, otherwise here comes the answer. Well, let's do the sums again. Now this gives us 6 is the input voltage, divided by 20 plus the 24.5, and multiplied by the 20. And if you plug that in, 2.7 volts is what you come out with. Superb. Okay, so that's that. Now, I just want to draw you back to this idea that you could only get this range between 4.5 and 2.5 from this setup. You'll only ever get a range. If you want to get a full range, then you need to turn to what's known as a potentiometer, and I'll show you why that is useful. Now, potentiometer, rather than having 2 individual resistances, you take a share, or you take a point between these two. In other words, you're halving this total resistance into 2 resistances. Now the reason why that's so useful is because if this were, say, 10 ohms from top to bottom, and you cut it halfway, you're creating 2 5 ohms, which means you get half of the voltage and half of the voltage. However, you can very easily cut it at any point let's say down here, where you might have, so of our 10 ohms here, you might have 9 at the top and 1 at the bottom, which means that, whereas here you'd get 5 volts out because it's an even share, here, of the 10 volts, you've got 9 up there, 1 down here, you've got 1 volt there. Or alternatively, you could have the reverse, and you could be working right to the top, where you have 1 ohm at the top and 9 ohms at the bottom, which means that you would get 9 volts. So potentiometers give full voltage ranges. And I think if you know that, you're way on the way to mastering this topic. Okay, I think that's enough for now.